So the panelists that we have are carefully chosen from a statistical viewpoint. It's completely unbiased selection, all of whom are hardcore systems researchers. Okay? So we have Saurabh Bansal, who is here, who did his PhD from Berkeley and was currently a faculty at IIT Delhi, and he works in the operating systems and programming languages area. Then we have Ranjita Bhagwan, who did a PhD from UC San Diego and has been with MSRI for the last couple of years. She works in the networking and distributed systems. Then we have Tim Roscoe, who did his PhD from Cambridge and is now at ETH Zurich. He's visiting MSRI here, and he works in operating systems and architecture. In fact, if you look at his website, he says, I do stuff, I do systems. And he actually does operating systems for future architectures. Yeah. And then we have Sudarshan, author of the well-known best-selling textbook on database systems, PhD from Wisconsin, currently a faculty at IIT Bombay, who works in database engine design. And then we have the last is Chandu Thekat, who did his PhD from University of Washington, was with MSR in the US, and then was the director of MSRI here for a couple of years. Now has gone back to the Microsoft Research in the US. And he's an expert in storage systems, especially with robustness and security considerations and so on. Yeah. So what I've asked each of them is to speak for a couple of minutes. We had initially given them 8 minutes, but maybe they will do it with a little less time, given that we are impinging onto lunch. But I'm sure that since you all love this topic, you won't mind sacrificing lunch in order to save systems research in the country. So what we will do is to request each of them to give us their viewpoints on this topic, and then we'll have a free-for-all with the audience. So, Saurabh, can we start with you?
Okay, thanks, Jayant. Thanks for inviting me to this panel. I'd like to make one correction.
Oh, sorry, Stanford. Sorry.
But no, that's perfectly fine. So I think I'll just introduce myself by just a short speech on what's my journey been and how I entered systems research. So before I kind of started systems research, I had done projects in theoretical computer science, computer graphics, wireless networks, communication, distributed systems, issues in trust and reliability. And I started my graduate school at Stanford, and I did some courses in systems. And I also got a chance to attend this conference called OSDI in 2004. And of all the kind of things that I had been exposed to so far, the ideas that I learned in the courses and in the papers that I sort of got to know about at OSDI, I felt the ideas in these papers were subtle, deep, and you had to have a certain level of understanding and maturity to be able to appreciate that kind of work. And most of all, the contributions of these papers were tangible and something that I felt like it was making an impact. And so I entered systems research, and I pursued my PhD in that area. Yeah, I think I can say a little bit about what I did. So I started during my graduate school working on my first project was on using dynamic runtime technique to assign types to values inside a computer system and see if those types actually, and how those types flow inside the system, and can I get some interesting properties about the operating system or the applications based on that. And I kind of got to learn a lot about the Linux kernel, the x86 instruction set. And eventually I did my PhD in a technique called peephole super optimization, which is a compiler optimization technique. As a faculty member at IIT Delhi, I have dabbled in areas of virtualization, optimizations in CPU virtualization and IO virtualization. And currently I spend most of my time in trying to kind of see if compilers, I'm back to my original work of super optimization, and I want to, the moonshot goal that I like to work on is basically, can we redesign compilers such that they are less complex? Today, GCC is 14 million lines of code, and it's not good at doing a lot of things that we wanted to do, especially in the coming years, given Moore's law and things like that coming to an end, sometime soon. So can we model a compiler as a large database of automatically generated optimizations using synthesis techniques? That's the gist of what I'm doing right now. Thank you.
Ranjita?
Hi everyone, I'm Ranjita. I work at Microsoft Research India. I'm a researcher there. So when Jayant asked me to be on this panel, I started thinking about the questions that he thought we should talk about. And I thought I'd start with some anecdotes anecdotes. So we hire interns from various institutions in India. And very often I've had interns who I've interviewed and I've told them, hey, I'm working on this school systems project. And they say, you know, I think I'd like to work on theory, machine learning. The system seems a little too easy, right? And this is not just once. And I'd also like to add that most of these are undergraduates from certain premier institutes in India, which the names of which start with I and end with T. But 3 letters before PGN says anything. So that got me thinking, you know, why did I get into systems research, right? Am I a person of low IQ? I don't think so, right? So before I go ahead, let me just ask the audience here, how many of you enjoy coding or programming? Wow, that's great. So one of the things is that really drove me into systems research was that I just enjoyed coding. And my first experience was, you know, in class 8 standard in school. I go to this museum, and there's this person teaching how a basic program looks like. And it was the first time I had even seen a computer forget about writing a program. And he wrote n equal to n plus 1. I said, what? How can n be equal to n plus 1? And I said, sir, you've got it wrong there. And he just looked right through me and went on, right? And so that's how it started. But then, you know, when I took up computer science, I just realized I just love programming. And so that was the first step. The second step was really figuring out that seeing something actually work well and targeting an existing problem that's out there. So very similar to what Saurav said, was very, very satisfying. And so when I went to grad school, I will admit that I looked at hot problems. As a student, you just normally do that. You look at a hot topic and work on that. So I enjoyed theory as well. I enjoyed graph theory, and I enjoyed writing programs. So I said, you know, how can I bring graph theory and programs together? I mean, instead of just theory, can I do something in programs? And that's when peer-to-peer systems and networks became hot. I said, this is great. This is what I'll work on. This is what I'll do my PhD on. And that's how it happened for me. So what I feel is, yes, machine learning is hot right now. IoT is hot right now. Deep learning is hot. But whichever topic is hot will always have a systems component. And thinking of the problem end to end and actually manifesting it in code is really what systems people do. And that's what I think I would encourage and request all students to look at in this room at least. Thanks.
Thanks, Ranjita. Timothy?
Okay, so I guess I've probably come furthest to be here, so I'll take up a slightly outsider position, I guess, and adopt some somewhat contrary views. First of which is my name is Mothy. Unlike Tim as trying to introduce me, my name is not Tim, it's Mothy. One calls me Mothy. My grandson calls me Mothy. The second is that actually my website says I build stuff rather than I do stuff, and I think that's an important part of systems research. However, the contrary position I'm going to try and argue for here is that I'm not sure I buy this the 3 pillars of computer science story completely. It makes a lot of sense, and certainly that's the way a lot of departments are organized. But I tend to view systems not so much as something in opposition to theory or in opposition to AI or machine learning or machine intelligence or whatever. I view systems as something slightly different. It's an approach rather than a topic, okay? It's not so much a kind of, you know, I'm going to look at networks or I'm going to look at deep learning or something like that. Systems is a particular way of approaching solving problems in computer science. And I happen to think it's a really fun way of solving problems in computer science. Ranjita and I were talking last night about, you know, we were supposed to be asking the question of, you know, why do we do systems? And the best answer we came up with is because we can. And so in that sense, what I think is great about systems, one of the things I think is great about systems, and the reason I love doing it, is that we can do anything. We can pull in ideas from theory, as Ranjita was saying. You can just, oh, you want to work on peer-to-peer networks? That's a pretty practical problem, right? They were real. They actually do stuff. They have to deal. They're fun. But, so you just pull in some graph theory because it's useful, right? Or you pull in some machine learning because it's useful. Or you pull in some programming language theory because it's useful, okay? But what you're doing, ultimately, is not so much studying a particular tiny topic or a particular limited area, which is, no disrespect to my friends in machine learning, but that's sort of, machine learning is a particular topic. What you're doing is applying a particular approach to a whole range of different problems that you can do in the course of your career. And it shows, right? So, the machine learning versus systems approach, I don't buy. Most of the people I know, but a lot of people who work in, the machine learning group in Google, for example, the people who wrote TensorFlow, an open source TensorFlow, they're all systems people, right? The people who actually run Google's wide area network, for example, to take another example, they're systems people, right? They publish at a wide variety of systems conferences in a wide variety of different topics. Okay, and so systems people work differently, right? What we do is we approach a problem by looking at it how it actually is in the real world, right? And the great thing about the real world is, the thing that makes it fun, is the real world's really messy, right? And all sorts of unexpected things happen when you try and do something in the real world. And so systems people tend to be a bit skeptical of idealizing a problem before they really understand what happens. Right? That's very different to the way that certain other fields sort of tend to operate, is you tend to idealize late once you can realize what you can get away with idealizing. And so systems is full of surprises, often what you think is the problem. And if you'd gone off and sort of, abstracted that away and applied some theory in the right way and solved it, you wouldn't realize this. That's actually not the problem, right? There is a different problem lurking in there, and as soon as you engage with reality, that other problem becomes actually much more interesting and you can solve it. And that's where you have impact. And so systems, to me, is special, right? We get to do bits of theory, we get to do bits of machine learning, we get to do bits of formal methods. I actually submitted a paper on formal methods last week, somewhat to my surprise. But ultimately, at the heart, we're systems people. We learn about the world by building systems that interact with the world, looking at how they interact with the world, what goes wrong, how to fix it. And we can pull in pretty much anything to help us in that respect. It's a wonderfully sort of free feeling. That's kind of why I love it.
Okay, thanks, Moti.
Thanks. I actually have some slides. Should I use those?
Yes. Yeah.
I don't know if people can see through us. We are not particularly transparent, but can I request people
So speak for yourself.
Good. I have a start by kicking everybody in the panel out.
They'll all run away if you're not.
So we are having a systems problem here. There's a theoretician, my dear friend Jayant, trying to fix it.
You had it on the other one? Yeah.
Okay, while that gets set up, I claim to be a systems person, and Ranjita said that she's not too dumb to do theory, but she does systems. I'll say the opposite. I got into systems because I thought I'm too dumb to do theory. Sort of. A better way to look at it is, each of us has a certain set of skills. And, oh, thanks. So we have a set of skills. And the question is, where are we going to get the maximum use out of it? And I could try to do theory and compete with a whole bunch of people who can do theory better than me. I could do systems, directly go programming stuff, and try to compete with people who can program 10 times better than me. But I think there's a nice niche where these two meet, where you find interesting theoretical problems in systems and build systems to discover theoretical problems and solve them. And I think that's a great niche which I work in personally. So the plumber's paradise. So this particular slide kind of says stuff which was already covered in Raghu's talk. So Raghu gave a very nice setup to this panel. He also scooped half of the stuff in this panel. And so Ranjita said, we want to work on a hot area. The problem with working on a hot area is you tend to get scooped. And so I will also advise you, say, don't work on hot areas. Work on areas which are going to be hot 5 years from now. Okay, so you have to predict, you might go wrong, that's okay. And it's particularly true in India, where we have a smaller number of grad students. We cannot bring hordes of people to work and day and night on a problem and get things out before the others. So it actually pays to pick problems wisely. So if you see what was hot over the ages, in the 90s, web, IR, massively parallel systems are great, ML. The problem today is that AI is eating us all. AI, as we heard from Janet's talk, was hot long back, then it vanished, then it came back with a vengeance and is eating everybody. So there's a lot of angst amongst us systems people saying, what is going on? What should we be doing? And it's actually hits home. For example, we have the COMAD conference on databases. And the number of database papers in COMAD was a pure database conference at one time. Then we widened to include ML, IR, and other related areas. But in the last few years, the number of database submissions to a COMAD conference has gone close to zero. And there is a serious problem that in India, at least, this is an India specific, it's an international conference. We do get submission from outside. But the number of people in India working in systems has gone down sharply. We are trying to hire database and systems people in general at IIT Bombay, and we are not getting enough people out there. So there is a problem. So the next question is, how does one solve this problem? You can use optics. How do you make plumbing look cool? Let's accept we are plumbers. How do you make it look cool? Well, this follows up from the end of Raghu's talk. Try to make it look sexy. Does it work? Well, I'm a dad, and I know that dads don't look cool to their children. So look what happens. And this is a bunch of people who try to use cool new technology, MongoDB, React, this, that, throw everything together in a system, and you have this horrible monstrosity, and you don't know what the hell it's doing, you can't deal with it. Okay, so you don't want to be cool for the sake of coolness. So the deeper issue in motivating people is, what are the useful and challenging research problems? So there are two things. One is systems people are motivated by what is useful. So it has to be useful. That's why I got into systems. And the other thing is, what is the challenge? Is it just a bunch of coding? Or are there deeper challenges which make it worthwhile doing a PhD in that area? So I don't have all solutions. We have already discussed some of these. Except that we are plumbers, do high-tech plumbing. This is a picture from a Japanese toilet. So let's do that, maybe. Or maybe we should look for moonshot challenge, the hard challenges. What are the hard challenges? And I would submit that many of the things we have been doing, these are all old challenges, but they're all still hard challenges. Coding, right? I mean, how many people in the world are coding? How many of people should be coding? Or should it be much easier to build stuff which you want, your apps, without coding? What about performance? How much effort is going into making stuff work properly with good performance, or just build systems which don't perform? Scaling. All of these are challenges which you need very smart people to build today. But can you build systems that will do all this for you? And there's a whole lot of new tools which are out there today. DSLs have been around, program analysis has been around, but there are better tools using these techniques which you can use today. SMT solvers, program synthesis, wonderful techniques which have a lot of interesting application in the systems area. And of course, there's AI and ML. It's eating us, but hey, we can use it too. And last but not least, let's look for India-specific challenges. What are these challenges? We have huge scale in India. This is the Aadhaar thing at the scale of billions of people. Affordability is a huge factor. So a lot of interesting challenges here. And we can motivate people. And Raghu already used this motivation. I got scooped again. Open source is a great way of motivating students to actually go build stuff. And we are sort of starting to do it like Microsoft in academia in India, but we should be doing a lot more. Okay, I'll kind of stop here. This is just a bunch of projects which we have been doing. I think I'll skip this in the interest of time. Okay. Thanks.
Thanks, Sudhir. So you could have your seats back. So Chandu, you have the last word.
Right. So first thing, if Moti can change his name, I can change my field. I don't do storage systems. I used to do that. But I think of myself as an operating systems and networking guy. AI and ML are not eating us. We are the mother of all sciences in computer science. Because if there is no systems, you are not going to be able to use that computer of yours. Trust me. And this is how I got into computer science. Computers were large in my days. I mean, the normal ones would fill up a big room. The reasonable ones would be like a refrigerator. And they had blinking lights and flash. And I didn't know what made them work. And it's by working in systems that I discovered how to play with them, how to manipulate them, and later come to understand how they work and invent new things on them. And that's a joy of creation you do not want to miss. And I guarantee you, no amount of staring at equations is going to give you that joy of creation. So I do not, you're missing a lot of fun stuff. And I was telling Moti, I don't trust anybody who hasn't written an interrupt driver or who doesn't know how to deal with concurrency. You don't really know how the computer works. There is a difference in doing systems. It's not a second-class discipline. It has got scientific rigor. You have to actually have repeatability. You have to do theory on it. You have to understand queuing systems to measure performance. There is a lot that goes into a systems, into doing systems. Systems is a way of life. It's an approach. It's not something that you want to shy away from. It's the most glorious thing you can do in computer science. Make that computer alive for people to use it. You may use it. AI and ML today seems to me like VI and Emacs or Excel spreadsheets. They are the dominant application so that people can do what they want to do, and that's great. But if you want to make this machine work, you need to do systems. And without systems, there is no computers for you to use. And if there's not enough people doing systems research, when those of us who are getting old die, it'll be a sad place. So, okay. Jayant asked us to do two things: the joy of doing systems and how to encourage systems research in India. I haven't spent a lot of time doing computer science in India. This is a fact of the matter. I was an electrical engineer by profession when I was in India, then I went abroad. But I've noticed, and I've been in an industrial lab for all my life, and I've noticed that of late, the Indian students who apply to our research for faculty for positions as full-time employees are mostly theorists. We rarely get Indian students, male or female, who do systems. This is somewhat different from what I remember when I was going to graduate school and did that. And I have a theory, and this may be wrong. In the 70s, 80s, and maybe in the early 90s, we didn't have a lot of computer science department for the undergrads in India. Most people who were good academic performers did engineering, and many of them did electrical engineering. And we learned to build operational amplifiers, or rather use operational amplifiers, build music systems and this and that. And we were all people with soldering irons in our hand who built what we thought were complex systems, and we thought of ourselves as engineers. And then when we discovered computers, it was natural for us to bring that mindset of a curious, disciplined engineer into this field. Today, when computer science is so prevalent here, I have a feeling that people think of computer science as a mathematical discipline rather than an engineering discipline. And I think that's unfortunate. And if you do that, you will lose your desire to do systems. So I encourage you not to think of computer science as a mathematical discipline. You don't need a computer. Let me remind you, a Turing machine is just fine if that's what you want to do. But there is a reason to have a computer, is to actually do something. And if you want to do something there, you have to do systems. I will stop now.
So if I could just paraphrase what Chandu said, he said that anybody who has not written an interrupt driver is computationally illiterate. So that is the opposite of what Raghu said earlier about statistics. So So I think they've all made their points very well. So maybe we could throw it open to the audience to ask us your pet question, especially those in the student community here who are trying to decide which way to go. If you had any questions to the panelists, you could, this is your chance to. It's okay, we won't grade you on the questions, so you can feel free to ask. There's a question here.
Yeah, so till the time the students think I can ask a question. So I'm Monojit from Microsoft Research and I work on AI. I used to love coding.
That's right.
Okay, so my question is, I was kind of expecting that at least one of you will mention, I mean, we hear this these days a lot often, that, you know, boundaries between disciplines are disappearing. So there is actually no difference between systems and ML. Actually, I collaborated with Ranjita with a couple of projects where I was doing the matrix multiplication part and she was, you know, together we were trying to do packet classification and stuff like that. So do you believe that these boundaries have been amplified somehow, or people really view things like this is system? One way is like you said, no, you said, Sudarshan, conferences is one way to label things. But are there like other ways of strongly labeling things which are like deep ingrained in computer science people's mind?
Anybody? Mati, you seem ready to go.
Yeah, you go, then I'll go.
Sure, yeah. Again, you know, I'd go back to what I said earlier, right? Systems people have been used to just trampling over boundaries for a very long period of time, right? We've always been able to do this. And I think that's something that's different about systems in computer science than other topics. You see this actually in other fields of academia. There are certain kinds of topics in academia, you know, not in engineering, but in, you know, social science and stuff, that have just quite happily ignored boundaries. And they've often had the highest possible impact. You know, systems is, you know, there are a bunch of systems conferences, and you should go off and look at the program, right? For a systems conference like, you know, OSDI or NSDI or SIGCOMM or something like this, right? And you try and figure out what the topic is, right? The answer is no, there's not much of a topic. SIGCOMM is much more network-oriented. OSDI is, it used to be more operating systems-oriented. There's a lot of database papers in there now. The point is that they're all systems papers. If you can figure out what's in common about those papers, then you've got it, right? And you've sort of figured out what it is. So, and at that point, you'll probably realize that it's the cool place to be. Chandu's right. It is the foundation of everything in computer science. You know, computer science is the study of a product, an artifact. It's a thing that acts socially. That thing's called a computer. And those things are built by systems people. I just want to say one other thing before I let Chandu go, and then I'll shut up. You know, coming here from, you know, a country that treats computer science and systems research in particular very differently, I'm amazed at the degree to which many of you guys are apologizing for being systems people, right? If you want systems research to get, you know, a better profile in India, step one, stop bloody apologizing for it, right? It's something to be proud of, right? It is the basis for the entire field, right? You know, it is a great thing to do. It is, you know, theory in computer science follows systems, right? Most of theoretical developments in computer science have been people trying to figure out how to formalize what these systems people have already figured out, right? And generalize it and abstract it. And then the systems people come along and say, oh, that's great, we'll use that, right? And there's that very fruitful interaction. So much of it starts with systems. And so, you know, don't apologize for it. Don't have this kind of, oh, well, plumbing. It's not bloody plumbing. Right? It's building the whole damn building, right? Everything else is just living in it. Right? Without systems, there is no building. Everybody else is just wandering around in the building trying to do something. I'll be quiet now.
So let me respond to that question. I completely agree with Mati, as you can probably imagine. But the reason I think we have these specializations is, I think, something different. And it came to me, and I'm sure you have seen this yourself. My daughter played in the snow a little too much, and she's got chilblains on her foot. She's 15 years old, so the question is, what do you deal with it? How do you go? Do you go to the chilblain expert? it's hard to find one in California, or do you go to a pediatrician? And you have to bounce back and forth. And I realized that computer science, like medicine, has become so rich and so pervasive in our society and in our life that we've had, by sheer lack of IQ and brain capacity, we've had to specialize. And that's the only reason I think we have specialists. I've been fortunate to have interacted with a great many number of pioneers in computer science. When I was in graduate school, I met Bob Floyd. I used to take classes from Knut as well. And both of them, although you might think of them as theorists, were consummate programmers, and they were consummate builders of systems. Butler Lamson works equally well in theory and practice. Chuck Thacker, who built the Alto, does a whole lot of things. He writes beautiful software. But as time has gone by, the amount of material that we call computer science has increased. And I think it's very difficult for one human being to keep track of all of that. So either spatially or temporally we divide it. By that I mean, temporally you could work on different topics over your career in different fields, or you just make a choice and you divide and you decide you're going to work in the same place for the rest of your life. But I think that's just an incidental thing. We shouldn't let that stop us from doing that.
So, yeah, I just have a small comment to add to Monajit's question. So he asked whether the boundaries have become stronger, and I think the answer is yes, especially within India. I've been at Microsoft Research for almost 10 years now, and I have been working with folks across Indian institutions over these 10 years, and it does seem that that divide has grown. So the number of people who say, hey, I want to do machine learning and machine learning algorithms, and I don't want to look at even systems aspects of that has definitely grown. Now, why that is, we can debate later. But
Yeah,
Yeah,
I'd like
so Moti, we're not apologizing about the plumbing part. We're just saying that without the plumbing, nothing else runs. So you require it to run. And also the problem here is that the student community especially has been almost hijacked completely into the ML world. So we are just trying to make sure that they get the right spin on the story.
Just one small point. Do you know how much a plumber makes in the US compared to a doctor in an emergency room? So
I would like to just respond to Monojit's question. I mean, I kind of, when Moti says that systems is an approach and not an area, it totally resonates with me. And I think all of us should, I hope that all of us can feel confident enough to say that I am a systems researcher. Even if you're doing ML or even if you're doing whatever else, you should be calling yourself a systems researcher. And by that I mean, if you're doing matrix multiplication and if you're showing results on, this is a speed up here, it would be great if you know how exactly it works all the way down to the L1, L2 cache or something like that. So, I mean, that's the whole point. I mean, we are not, yeah, so I guess sometimes it's a little, dissatisfying to see people talking about performance and things like that without understanding the whole stack. And I think it's important to do that.
Yeah. So I think this idea that you can work in one subpart of systems is history today. I think we kind of were able to do it for many years thanks to Moore's law. As a database person, I could say the hell with parallel databases because tomorrow the CPU is going to be twice as fast and a centralized database will do everything that I need to do. And we were able to do this for many decades, but now it's hopeless. So what I see increasingly, I have a database perspective, but I'm sure this same thing is true for other systems people, is that if I want to build a good database system, I need to understand architecture, I need to understand the memory hierarchies, I need to understand cache coherency, and increasingly I need to understand GPUs and SIMD. Then I need to understand networking because one single machine cannot handle it all. Then I need to move up to programming languages because I don't want to actually code all this at the lowest level. I want to be able to use tools which can compile things down to this. So I need to understand what Govindarajan is doing, maybe use some of the tools he has built. But I cannot remain oblivious to what is going on underneath. It's exposed, and I need to understand it. So in a sense, I think a systems person today has to be quite different from a systems person of 10 years back. And I think that's very exciting to me, that there's a lot of stuff, a lot of depth which is coming in, and I love it.
Should we go to one other question?
Can I just say, I add something to that? Because I think that, we've just heard different ways of saying something incredibly important about systems, which is, if you are a systems person and you are writing, some JavaScript or something, or some SQL, right? If you're a good systems person, you know exactly what's going to happen to that code, from the compiler through to the instruction set, through the way that it interacts with the caches, with the TLB, with the memory management unit, with the I/O subsystem, with the DRAM controllers, how it interacts with other threads, with the operating system, with the scheduler, all that sort of stuff. You don't know it all, because this is way too complicated for anybody to understand. But you have a good picture in your mind all the way down to the transistors. And most people in computer science don't have that. And that's why systems people, in the US earn at least an order of magnitude more money than plumbers, probably 2 or 3 orders of magnitude more money than plumbers, because that skill is incredibly valuable, and it's quite rare.
So to again paraphrase that, it's deep understanding versus deep learning. That's fair.
Yeah, so I just like to offer a theory, being a theoretician, about this lack of popularity that Ranjita mentioned, and maybe the general low prevalence of systems research in India. So I think my impression is that good systems work needs larger teams. And I think that's what we lack even within the big departments. I think, Microsoft Research, I think, is an exception because it is a coherent research group which has a lot of collaboration within the Indian team and across research groups in different labs. My impression is that even within Indian departments, people tend to work in very small groups. And partly what Sudarshan was saying, that as a systems researcher, you need to have a big group, you need to talk to other groups. And I think that this works more effectively, these small groups working in isolation. I think it tends to be easier to work in certain areas and not in others. And I think this is my explanation as to why, in a sense, students don't, it's a self-propagating thing that you don't have a big group, you don't have a pool of, don't have a hierarchy of people working to do implementations, test out things. And I think this tends to also make it then less effective, and then less students want to join and so on. This is my take on it.
Go ahead, after you.
So I'd like to respond to that. I built a great number of systems in my life, some of them deployed in real life. I've never worked on a team for more than 3 people. It's easy to confuse systems research with engineering and product engineering. To deliver a product that is rock solid, that will stand the test of time, requires a big team. To do systems research requires a far less team. You can do a lot of damage with 5 people in systems research. Some of the best, if you just scan the SOSP and OSDI proceedings in the last 5 years, you will form an erroneous opinion on what it takes to build systems. If you scan for the entire duration, say a decade or 15 years, you'll find substantial systems built by small teams. And I think it still can be done.
Actually, Chandu, I think there are papers in the recent few years which have 2 authors, 3 authors as well. Yeah. So that's proof that it can be done.
I'll take the opposite side. I'll say that even Microsoft feels it's too small to do systems work now, right? We heard Raghu's talk, and he's talking open source. Why? Partly because of market forces, but also partly because there's an ocean of people contributing towards systems. And I think this can help change this picture which you talked about. What you said is true, historically speaking, but today you can take open source code and add some cool features to it, do research on that, and you don't need a large team. You can be 1 person or 2 people working on it. So I think the thing has changed, and the stage is now set for Indians to contribute a lot more to systems.
Take one more question, I think.
Yeah, hello. This is Saurabh Joshi from IIT Bombay. So in the PhD interviews, what we found when we asked students that in what area they are interested, statistically 4 out of 5 people say that machine learning, data science, and this is connect with Ranjita's question that people look down upon other system area, or Sudarshan's point of view that not having enough good people in other systems area. And now what I asked the panel is that what are the steps that we can take at maybe undergraduate level, either in the curriculum or outside the curriculum, to sort of create a diversified workforce or a diversified research interest in this?
I have a drastic solution. Long ago, in the 80s, if you went to Cambridge Systems Laboratory and enrolled as a PhD student, this may have been before Marty's time, you didn't get a workstation. You were told, over there is the monitor, over there is the CPU board, or here is the RAM. You go make one. Okay, so I think you should tell your PhD students after you hire them, the guys who want to work in machine learning, that we don't have a computer for you, you can make one. And go to open source and get some software and run it, and maybe then they will appreciate that there is more to working on a computer than than at the higher levels.
So Saurav, anything at IIT Delhi that you have done especially?
Yeah, so I mean, I think it's an important question, and unfortunately I don't have ready answers, but definitely events like these where we are actually actively talking about the joys of systems research is a great start. And in general, I think, the operating systems course is a good place to actually introduce students to systems building. And unfortunately, most operating systems courses are not that level of rigor in systems buildings yet. I hope things are improving, and I think it's going to be a gradual journey.
So I have a couple of suggestions. I don't know, I'm not as drastic as Chandu's, but let's say you hire those PhD students who say they want to do machine learning. Maybe mix them up. So in the first year or second year, right? When you put them in rooms, let's not have students in the same lab sit in the same room, right? Mix up system students with machine learning students. We know that physical proximity means they'll talk more. And maybe that will gradually change how people think. That's one suggestion. And the other one is, 2 days ago, we were chatting, and I'm not sure if all institutes have qualifiers here for PhD students. So if you have if you have these qualifiers, and you make sure that there are some core course requirements that students have to take before they qualify to do their PhD, that would be great. And it would include machine learning, it would include systems, programming languages, databases, if, I don't know databases.
It's mandatory.
But you get my drift. Those are 2 suggestions I thought of.
So Moti, anything else that you do in Zurich that has allowed you to keep the beast at bay?
We don't keep the beast at bay. The beast comes to us and keeps asking us for advice. Okay. Right? So seriously, we just hired a really great machine learning guy from Stanford, Che Zhang, right? And he turned up and he said, "I want to be in the systems group." Right? He, at his interview, you start standard interview questions. You should be ready for these if you're students. Standard interview questions. So if you come to our department, what would you work on? What would you like to do? Do you like to collaborate with? And he said straight away, I want to be in the systems group, because I think that most of the really difficult problems that we have right now in machine learning are essentially systems problems. He worked to some extent at the boundary of machine learning and systems, and he came and sat in our group, and he's in our group, and our students all sit in, mixing up in different offices, which really does work. And so that's just how he thought, right? As an ML guy, as a junior faculty ML guy. I think, though, you can start much earlier, and I think that there are things about computer science education, particularly the operating systems classes. They vary wildly around the world, and you look at operating systems classes at places like Carnegie Mellon, and I'd like to think ETH Zurich and stuff. They're wildly different from operating systems classes at maybe some lesser universities that I won't mention. There are people who teach operating systems using Java, This to me is extraordinary. You know, what are the hard problems in operating systems? Concurrency, memory management, and protection. What does Java give you? It automatically does concurrency, memory management, and protection. Why are you teaching operating systems in Java? So we do teach, like CMU and other places, we teach assembly language. Not much, but enough assembly language so people understand it. We teach a bit of processor design. We teach C. We teach systems programming. We teach concurrency in the first year of undergraduate. Parallel programming is the first year of undergraduate work at ETH. Then there is an operating systems course, a networking course, and databases course, all of which are taught by systems people. And that really, you know, helps people to get, it helps the students to get a grounding of what these computer things are. And that's something that you know, certainly the people who employ our students really value, is that an ETH student knows the whole stack, you know, all the way down, enough about it to get by. I think that makes a huge difference. We also do the qualifying thing at the master's level. It's a slightly different structure. But we have 3 labs that you have to do at master's level. And you have to pass them, otherwise you're out. And you actually get to pick 2. But we have an algorithms lab, which involves a lot of coding of algorithms. We have a computational intelligence lab, which is about coding up machine learning stuff, but actually has a strong systems component. And we have the advanced systems lab, which is about building a real computer system and analyzing its performance. And that also makes a huge difference. And so systems is a pretty popular area at ETH. It's a third of the faculty. And that's really reflected in the student numbers as well.
You want to take more questions, or I'll leave it to
We
Jain?
probably have just the very last question here.
Okay, you have the mic, Venkat.
Oh,
So.
sorry, sorry, I didn't see that.
Sorry, we'll take your question offline. Venkat.
No.
Okay.
Maybe we can ask them the question over lunch.
Okay, I'll ask a very
This is-
quick,
yeah,
okay,
yeah.
very quick question. This is actually, Chandu touched on this very briefly. Could some of you articulate very clearly the difference between computer systems research and engineering? I don't mean these, you know, the product development, long-term testing and all that, but intellectually, what's the difference between computer systems research and engineering? Because I think that's a confusion a lot of students have, at least in India, and they perhaps think it's just engineering or something, and therefore they don't do it. Maybe you can clarify.
If I can go first. So my take is research is about how to do what you're doing better. So you can do computer systems engineering, you can have a particular process for software development, you can have a process for testing. But if you can automate the whole thing, if you can do it better at lower cost, you know, wouldn't that be great? And that's where research comes in, how to do things different from how it is done. Whereas companies have to deliver tomorrow, they can't afford to look 5 years down, and they have to work with engineering. So I would say that's my take on it.
So I think I would just say that it's research, and research automatically means there's risk. And if there's no risk, there's no research. That's my understanding. And I mean, even the first time an aeroplane was developed, it was engineering, but there was risk associated with trying to do something which was pushing the boundaries. And I think that's what I would say.
Yeah, I often sort of explain it to my students as if you're writing code, if you're doing software engineering, you have a particular problem to solve, right? It's a particular problem at hand, it's very concrete, it's a particular problem at hand, and what you want is a good point solution to that problem quickly, right? If you're doing systems research, you are also building a large body of software to solve a particular problem, but your goal is different. You're not coming up with a point solution. The reason you're building the system is to understand the problem and understand a much broader sense of the problem so that you can derive more general techniques and insights as to what the trade-offs are, what things work, what things don't work, what unexpected effects may cause problems when you try to apply a solution from somewhere to somewhere else, and so on. So it's exploring both the problem space and the solution space. And we do that in systems by building systems and figuring out what we're doing while we're building the systems. I think that's how I would distinguish it from engineering.
So I think of systems research as discovering the nature of something through experimentation. So you are trying to understand something that you really don't know. You're devising, you have a theory behind why you think it is it's the way it is. You devise an experiment to test your hypothesis, and now you have to do the experiment that actually requires debugging, building, and so on and so forth. So most systems, what I would consider more systems research, has a research component in it. That's what distinguishes that from engineering. Engineering is efficient. It tries to gain efficiencies. It tries to gain reliability, reproducibility, and that sort of thing, so that when Microsoft ships a product, we are reasonably certain that thing is not going to, blue screen. By the way, the blue screen happens to device drivers written by other people. So I think that's how I characterize systems research. There is a hypothesis, and there is an experiment, and there are learnings from that experiment, and that we can communicate to other participants and practitioners.
We actually have one of the people who killed the blue screen sitting right here, Sriram, and I think that is fantastic research, and maybe Sriram can say something about it.
Actually, as a PL person, the way I always thought about systems was that, and I think it's just not me, several people in the PL and formal methods community, when we try and invent techniques, we first publish in sort of the more PL conferences, and when the thing becomes real, and it works on real things, then we dare to submit to system conferences. I have a tremendous regard for systems, right? That's how, as a PL person, right, I think about it, is that, now I'm playing in my sandbox, and when it becomes real, that's when I dare to come to you. Yeah. Yeah.
So we need to spread that shock and awe amongst the student community. That's what you mean. Okay, I think we'll have the last.
So actually, I just have one quick point. While
very
the
last
mic
one.
is being run to him, let me just address that question. I think students here might just be a little confused by that whole discussion. That's what I feel. So the way I would think of that question, systems research versus engineering, if I were an entry-level student, right, I would go and read systems papers, SOSP, OSDI, NSDI, SIGCOMM, and a bunch of these databases, VLDB, Sigmod. And then I would try to filter out what in those papers really makes them tick. There'll be either a cute idea, or there will be some measurements which, over some not that cute an idea, which show a huge, huge win. So filter that out. That's what is systems research. So it's sort of a backward definition in some sense.
Okay, so we'll have
That's
the
a
last
machine
question.
learning definition.
My name is Neeraj Joshi. I am actually third year engineering student, and I had the most silliest question that what exactly is system programming, because that's the biggest question we students have, because we have subjects like system programming and operating system. In operating system, we study the working of operating system. In system programming, we design compilers and all, assemblers. So the concept of system programming or system research is not clear in the students, and also there is nobody to motivate us to go into system research or to go into system programming. Someone comes and says that you should try for AI, you should go for machine learning. Nobody comes and says that you should go for systems research. And also, just one thing, one more point is that in system research, we already have systems created, like we have a compiler, we have operating system. So students think that why should I create new one if I already have one? Nobody thinks that I should create the better one. So that I think is a problem, and what should be the solution?
Okay, so I think I'll answer your last question, which is, people think that systems are already there. What's there to do there, right? And I would just say that, in my understanding, systems research today is much, much more exciting than let's say any other area of research, without picking on any area, because there's so much to be done. Given that, so for many decades we were riding on the back of the Moore's law, the clock speeds were getting faster. Now the transistor count is still doubling, but even that's going to stop at some point. And so the software stacks have to evolve, both at the compiler level and the operating system level. And you already see lots of people chipping at different positions. And I think the next decade may be one of the kind of most innovative decade in this area. So I'm definitely very, that's my...
I've refrained from plugging my own research so far, but if you look at hardware today, right, you look at what people are currently building in hardware, what people are currently using in hardware, there is no operating system for it. It doesn't exist. What you have is an operating system that runs on a tiny part of that hardware, and then you've got essentially a bunch of other things sort of lashed together with duct tape. And so we do not have a working operating system for modern hardware, right? We do not necessarily have a terribly good compiler for modern hardware either, okay? So it may look like this, but you just believe the product hype if that's the case. If you really want motivation for why to go into systems, I mean, I could say, come to Switzerland, but I think that's probably a better question for my colleagues at Indian institutes to answer as to why people aren't telling you that, because it's easily the coolest thing to do.
So I'd like to address your first question, right? Systems programming. I did that course too when I went to undergrad, It's assembly, programming, and that's what you think is systems programming, right? But at that time, that was, oh my God, I won't tell you how many years ago. The internet was not accessible. The web is accessible to you. So you can actually Google or Bing systems programming, and it'll tell you what is systems programming. It is not that course. It is partly that course, but it's not just that course. So I'd recommend you do that.
Actually, if you do a Google, Bing, DuckDuckGo, do systems programming James Mickens, and you'll read an interesting article on what it means to be a systems programmer.
So I want to add one little point to that question. I think if you take any reasonably complicated system, whether it's a compiler, a database, or whatever, and look at it a little more carefully, you'll find huge ways you can probably make a difference if you know it well enough. But if you think of the compiler as something that translates from language A to language B, yeah, it probably does an adequate job. But there is a lot of complexity hidden inside it. Same thing with databases. You throw some data into it, it puts into a table, you make a query. There is a lot of complexity, and there are a lot of interesting intellectual challenges out there, which fall right in the domain of systems research. So don't go by the black box transfer function mentality. Go in there and look at what's in there. And I think you'll be surprised at the richness in it.
So let me answer that question. So it's natural for students to want to do the latest, greatest new technology that comes around. And indeed, many students should do that. But as an analogy, look at the internal combustion engine and look at cars, right? I mean, cars were invented now, 140 years or so, nearly 150 years back. But they're still evolving. You would not buy a car which was built 15 years back today because it's just not good enough. It may be 10% worse than today's car, but you still wouldn't buy it, right? And even areas in systems which have been around for a long time, they're seeing continuing improvement. And in fact, it's much more. It's not 10%. There are much bigger improvements even in the last few years. So I think it should not be the case that everybody should go do the latest, greatest, because it's too crowded. I mean, look at what is happening in the ML community. There's so many papers coming out, people can't keep up. People are putting up stuff in archive because they are afraid that if they don't put it, they'll be scooped before they submit it to the conference. And what does each paper do? If you see the delta of a paper, from what I gather from my colleagues who work in that area, they're really tiny deltas. People are doing small things in that. Do you really want to get into that? I mean, this is not something which people will tell you, but you can be a big fish in a relatively small pond, or a tiny fish in a pond where everybody is biting at each other. But the way I look at it is, don't get into this into this rat race of fish. Look at what value you can bring, and to society, to customers, and then you will do well. You will be rich and do interesting technical stuff.
Right. The last word?
This is sort of, again, to the motivation question, and this is probably more the faculty people in the audience. My experience when I moved to ETH was that as a systems person, I'd recognized that modern operating systems didn't work on the hardware that was coming down the pipe. And myself and a very good friend of mine who was a colleague at Microsoft Research at the time, Paul Barham, decided that the world needed a new operating system, or at least needed a new way of thinking about how to write operating systems. And so we started writing one with students and postdocs and people at Microsoft. And we're still working on it. It's been a very useful vehicle for research, lots of publications, all that kind of stuff. But my goodness, the reaction of the undergraduate students at ETH when they heard that somebody, a research group in the building, initially in conjunction with Microsoft, was writing a new open source operating system from scratch that was very different from Linux and very different from Windows, deliberately so, and we're serious about it. My goodness me, the students were breaking down the door, right? We had so many people who wanted to come and work on it. And it was a huge motivating factor. because it's an exciting thing to do if you just actually tackle something big like that. That's the great thing about systems research.
So Chandu was worried about systems researchers dying prematurely, and we didn't want to have that because of lack of lunch. So I think on that philosophical note, we will break for lunch. Before we do that, please thank our panelists for an extremely vigorous and entertaining session.